He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
Ngā mihi nui and welcome to Elemental, a chemistry podcast from RNZ. I'm Alison Balance.
And I'm Allan Blackman from the Auckland University of Technology. And in our always colourful exploration of the periodic table, we are up to episode 70, Rubidium.
Anything to do with rubies? I'm thinking rubies are red.
Sorry to disappoint. Not quite. No, there's no rubidium in rubies. That's not how they got their name. They are aluminium oxide with a little bit of chromium in there. And if we go back to the chromium episode, you can listen all about that.
I should have remembered that. Oops.
So rubies, in fact, get their name from the Latin rubor, meaning red. But rubidium is aptly named from the Latin rubidius, meaning deepest red. But in its own way, it is kind of precious. Despite being fairly abundant, it is rather pricey. So it sells for around about 23,000 New Zealand dollars per kilo at the moment.
Oh, don't think I'll be popping out to buy any time soon then. Vital stats, please.
Okay, so elemental symbol Rb, atomic number 37, which puts it on the left-hand side of the periodic table down towards the bottom of Group 1. And it was discovered in 1861. And it holds a place, I guess, in the discovery of the elements because it was the second element that was discovered by spectroscopy, the first of which was cesium. And if you missed that, you can find our episode about cesium in our back catalogue. So, discovered by Robert Bunsen.
Ooh, I've heard of him. He's the man of Bunsen burner fame.
Indeed he is.
Yes.
And Gustav Kirchhoff. Ringing any bells?
Sadly, no. Look, I do usually only manage one chemical fact per episode, if I'm lucky. So, no, tell me about Kirchhoff.
Yeah, well, I wouldn't call him chemistry, really. It was more physics, but he is the Kirchhoff of Kirchhoff's laws fame.
Which is what exactly?
Which is, if you remember back to your high school physics and remember those circuit diagrams and stuff, and this is all to do with current and voltage in electric circuits, which we're not going to go into because that's physics. Anyway, so Bunsen and Kirchhoff, they used the newly invented spectroscope to look at the atomic spectra of elements. And so what does that all mean? What they did was to heat the material, or a material, and in this case what they were using was a mineral called lepidolite. So they heat that in a flame, and then they look at the colours imparted to the flame by the elements in this particular mineral using the spectroscope. So we need a little bit of explanation as to exactly what's going on here. So here's some first-year chemistry for you all. So if you put any element, or in fact any particular chemical substance, into a flame, the atoms are absorbing energy. And what they do when they absorb energy is that they promote electrons from low energy states in the atom to high energy states in the atom. And then once they've got to these high energy states, then they don't really like being there and they want to get back down to the lowest energy state in any way that they can. So there's a number of ways that the substance can actually do this, and one of these is by emitting that excess energy as visible light. And not only visible light, but a whole lot of, I guess, invisible light like ultraviolet and infrared and stuff that we can't see. The wavelengths of light that are emitted by any particular element are absolutely peculiar to that element, okay? And so therefore, they can be used to unambiguously identify any element. Every element has got its own unique atomic emission spectrum, is what we call these things. So Bunsen and Kirchhoff were busy using the spectroscope, analysing colours in the flame, and they found a couple of beautiful deep red lines that they couldn't ascribe to any known element, and so that's how rubidium gets its name.
And since Bunsen and Kirchhoff also found cesium, which by thinking very deeply I seem to remember had blue spectral lines, they found it from the same mineral.
Yep.
I assume this means these two elements share some features in common?
They do indeed. They're both Group 1 metals, and rubidium sits above cesium in Group 1. And so being a Group 1 metal, that makes it soft, it makes it low melting, and it makes it very reactive with water.
So down that left-hand column on the periodic table, we've got potassium, which is also explosive in water, isn't it?
Yes.
So if you missed the potassium, you can go and listen to the earlier episode in Elemental about it. And sodium, which is coming up soon.
Absolutely, yes.
So, rubidium, is it useful or no?
Well, given its price, which is surprisingly high, no, there's not really many uses for it. So it can be used in atomic clocks, which are very, very accurate beasties, but its Group 1 underling cesium, directly below it, is in fact better, but in fact that's more expensive as well. But the cheaper rubidium clocks still do a pretty darn good job. They're amazingly precise, and they do in fact get used in global positioning systems. So what else about rubidium? We've got the rubidium-82 isotope, and that can be used in positron emission tomography, or PET scans, which may be familiar to some listeners. And we mentioned PET scans briefly in the lutetium episode, if you go back and listen to that.
Is that it?
Well, almost, but not quite. And in fact, rubidium's claim to fame, the one that really put it on the map chemically, I guess, is that it won Eric Cornell and Carl Wieman the Nobel Prize for Physics in 2001. And they got this because they were the first to make a Bose-Einstein condensate using the rubidium-87 isotope. So
I know this is a bit more physics than chemistry, but what exactly is a Bose-Einstein condensate, please?
Oh, I don't know. I'd say it's chemistry. You know, if it's interesting, it's chemistry. If it's not, it's physics. So we go all the way back to 1924. A famous Indian physicist, his name's Satyendra Bose, and he was doing some calculations on photons. And photons, hopefully, as many of you know, are particles of light. He was interested in these, and he'd done some calculations, and he sent his work to Einstein, and he extended the work of Bose to particles that are now called bosons, in fact, after Bose. So what he showed was that at very, very low temperature, bosons, of which the rubidium-87 isotope is one, should in fact spontaneously assemble into a new state of matter. What are bosons? Difficult to explain. So they are atoms that have got integer spin. Okay, so that means that their spins are 0, 1, 2, 3, 4, etc., etc., as opposed to fermions, which have half integer spin. And the big thing about bosons is that bosons can occupy the same quantum space. Unlike electrons, for example, electrons are fermions. And again, those of you who've done any first-year chemistry, you will know that you cannot stick two electrons into the same orbital with the same spin. So there's a little chemistry lesson for you all. Anyway, so the guts of this was that this was a prediction made way back in the 1920s by Bose and Einstein, and it took until 1995, in fact, for this to be confirmed experimentally when that particular Bose-Einstein condensate was prepared. So what use are these things? Well, you know, they are a new state of matter. They only exist at extremely, extremely low temperatures. And they're pretty much, at the moment, only of academic interest, but they may have some uses in quantum computers. And if you want to learn more about quantum computers, go back and have a listen to the niobium episode.
It's great that we've got such an excellent back catalogue of elements to refer to now, isn't it? It's like being a cooking show. And here's one we prepared earlier. And I also take from that calling someone a boson is not as much of an insult as I thought it might be. Anyway, the Elemental back catalogue can, of course, be found at rnz.co.nz/chemistry.
Or indeed wherever you found this podcast. So we're back next time with ruthenium. But until then, it's cheerio from me, Allan Blackman.
And me, Alison Balance. Mā te wā.